Okay, we've already looked at like a couple of applications of the orientation of the cross product. But now let's look at actually how we would cross product two vectors together. Like it's not just the geometry of the situation, the actual calculation if we've got numbers involved. Okay. The textbook definition for the cross product, it comes from the determinants of a matrix. But I prefer to understand that it comes from this, but then just sort of remember a rule instead. Like once you've done a few of these, it's a bit easier to remember. If we were going to calculate the determinants of this matrix, if we looked at it along the top row, remember we'd have the plus minus plus pattern if we were going to use that top row. So then that would be I, and then the determinant of what is left. Okay, so that would be A2, B3 minus A3, B2. Then for the J, which is this, remember I is just the top element, J tells me it's this middle element, middle row. You've got minus being applied, and then the determinant would be of these values, so it would be A1, B3, minus A3, B1, and then finally K, which is this positive, and then we're looking at this, so it would be A1, B2, minus A2, B1. And to be perfectly honest, like when I'm doing this in my head, the cross product, I actually just remember it like that. I just look at, cover that one up, and then it'd be A2, B3, B2, A3. Like you can just cover the rows up as you go. For the next one, if we cover up A2 and B2, it'd be A1, B3, B1, A3. You've only got to remember though that with this one it's a negative because it comes from the plus minus plus pattern. So just remember that cover up as you go, cover up that one, do the determinant, cover up that one, do the determinant, cover up that one, do the determinant. Okay, so let's try an example of actually using this formula to calculate the cross product. Okay, so for the first example, we're going to prove that when we cross product a vector by itself, or in other words, two parallel vectors, the answer is 0. So if I want to do I cross I, that would be 1, 0, 0, cross 1, 0, 0. Okay, so if we apply this rule, cover up the top row, you clearly see that they're all 0, so it's going to be 0 times 0 minus 0 times 0, which guess what is 0. Cover up the middle row, you've got minus 1 times 0 minus 1 times 0. I suppose with it being a proof question, I should maybe show where this is coming from. So that would be 0 times 0 minus 0 times 0. Okay, it's not your typical proof this, by the way, it's just to get us used to how this cross product works. And then for the last one, it would be 1 times 0 minus 1 times 0. So we end up with the vector, which is just 0, 0, 0. You could write it as just 0. Okay. This one's a little bit more interesting. Okay, so if we want to prove I cross J is equal to K, coming from the right-hand rule, which we discussed earlier, we've got 1, 0, 0, cross product with 0, 1, 0. Okay, so cover up, and then you've got 0 times 0 minus 0 times 1. The middle, don't forget the negative, 1 times 0 minus 0 times 0. And then the final one, we've got 1 times 1, hey, there we go, minus 0 times 0, which is 0, 0, 1, also known as K. Okay. Okay, so this is more getting into what we're going to need for the majority of the exam style questions. Like when we actually do the cross product moving forward, when we're looking at equations of lines, equations of planes, you need, what we really, like a really key understanding on this topic is that like if we have two vectors, so two numerical vectors, And if we cross product them together, we end up with a vector that's perpendicular to both. Okay, so this question is saying, find the vector perpendicular to both of these. So imagine we had one vector, which was 2, 1, minus 3. We had another vector, which was minus 1, 3, 5. Then if we cross product those two together, the new vector that we end up with is perpendicular to both of those original vectors. Okay. So we've got 2, 1, minus 3 cross producted with minus 1, 3, 5. Okay, cover up and work out your determinants. So that would be 5 minus 9 minus 10 minus 3 and then 6 minus 1. So we would end up with 14 minus 7 and 7. Okay, so that vector there would be perpendicular to both of these. Alright, it actually says find a vector perpendicular, so if all we care about is the direction of the vector, you could write any multiple of that, like any answer. Like you could also write 2 minus 1, 1. That vector would also be perpendicular to both of those, and that would maybe be a little bit easier to work with later on in the question, just depending on what comes next after we've done the cross product. But we'll see that, later. Okay, but I'd just leave it like that for now. But just realise that any multiple of this is also perpendicular to both of those. Okay, example 3. We're given two vector equations of a line. Okay, so if you remember, you haven't seen this for a while, but if we've got it written in this form, like one line, that tells me a point on the line, and this is the direction of the line. That tells me a point on the line, and that tells me the direction of the line. Okay. Now what's going on here, if we try and visualize this, we've got L1, which would be maybe a line that looks like, doesn't really matter which orientation I draw it in, let's say we've got a line L1 there, we've got a line L2 there. Now what I've noticed here, that these two lines actually share a common point, don't they? Like, imagine if lambda was 0 and if mu was 0, then we know 1, 5 minus 2 is a point on both of these lines. So these lines are not parallel to each other, they're clearly pointing in different directions. So they both pass through that point there. So that point there is the point where the two lines intersect. Okay, but they're clearly going in different directions. Like this one's going in the direction 3 minus 4, 1, and this one's going in the direction 3, 5, 2. Okay, and what we're aiming to get is we want to find an equation of a line which goes through that point, but it's got to be perpendicular to both of these lines. Okay, so if I want to set up an equation of a line, there's two things I need to know, isn't there? I need to know a point that it goes through, and I need to know the direction that the line's heading in. So if the new line that we're trying to find is perpendicular to both of these, it's going to be heading in that direction, isn't it, which meets both of those lines at a right angle. So this is the direction of the line that I'm trying to find. Okay, and now obviously, because we now know about this cross product, like if we cross product these two directions, if that line's going that way and that line's going that way, if I cross product those two vectors, I get a new vector which is perpendicular to both, which is clearly going to be the direction of the line I'm looking for, isn't it? Okay, so this basically the problem boils down to cross product these two vectors, and that'll tell you the direction of the line that you're trying to find. Okay, so if we do that, you might think, well, which way do we have to cross product them? And technically it doesn't really matter, because like all we're looking for is a vector that's pointing that way. If I do, think about the right hand rule, so if I do L2 cross L1, So if I do L2 cross L1, that would be pointing up that way. But if I did L1 cross L2, and I'm sorry I can't say my hand that way, but if I did it the other way around, I'd end up with like the direction going that way. But it really doesn't matter. Like if I just get a vector going this way or a vector going this way, it's still describing the direction of the line, isn't it? Like, you know, imagine if I wanted to write this line, I could have also written that as -3, 4, -1. Like that line there is the same direction as that one. It's just that the lambda value would be slightly different. You know, it still takes you along the line, doesn't it? So it doesn't matter which direction we cross product them, because we're still going to get a vector which points in the direction of that line. Okay. So when we cross product these two, cover up, you'd get -8, -5, -6, -3, and then 15, -12. So I've got -13, -3, 27. Okay, so we're done. Basically, we just need to actually write down the equation of the line. So let's say therefore R3, oops, I should write it as R equals. So R3 would be point on the line. Well, we know the point it goes to is 1, 5 -2. Constants, lambda, mu, let's use a different letter. It doesn't really matter, I'll use delta. -13, -3, 27. Okay. And that will do it for this video, guys. Thank you.